Last time we saw that one way of solving an extensive form game is to translate it into the induced normal form and then search for pure strategy Nash equilibria. That transformation process involves enumerating all possible complete plans of action to get the full strategy set, and then we fill in the payoff matrix and identify best responses. In this particular example, we identify two pure strategy Nash equilibria. In one equilibrium, player 1 plays strategy A, while player 2 plays the strategy CE, meaning that if the game arrives at this decision node, player 2 will pick C, and at this decision node they would pick action E. And in the second pure Nash equilibrium, player 1 plays strategy B, while 2 plays DE, meaning that player 2 would play D if the game got here, and would play E if the game got here. But between these two Nash equilibria, one seems a lot more plausible when we think about the extensive form game. In particular, this equilibrium claims that if the game were to reach this decision node, player 2 would play action D. And in response to that strategy for player 2, it makes perfect sense for player 1 to choose B. Player 1's alternative of choosing A would lower their utility from 1 to 0. But the hypothetical that player 2 would play D at this node doesn't make a lot of sense. If the game actually got here, player 2 would do better by switching to action C. And so while this profile meets the definition of a Nash equilibrium, it fundamentally depends on player 2 making a non-credible threat to get player 1 to avoid this part of the game tree. And this possibility is part of the reason why extensive form games have a huge number of Nash equilibria, and why Nash equilibrium may not be the best way to make predictions in extensive form games. Instead, we can refine our equilibrium concept by looking at subgame perfect equilibria, where we require that the profile of strategies constitutes a Nash equilibrium not just for the entire game, but also for every subgame if we were to investigate from some decision node to the bottom of the tree. Since this game tree has perfect information and 3 decision nodes, it has 3 subgames, one of which corresponds to the full game, and 2 of which correspond to the 2 decision nodes for player 2. If we restrict our attention to the right subgame, only player 2 has a decision to make, and player 2's unique best response is to play C, and so the only Nash equilibrium here is for player 2 to use strategy C. And likewise, in the left subgame, the unique Nash equilibrium is for player 2 to choose E. And so now in the full game, a profile can only be a subgame perfect equilibrium if it uses action C in this subgame and action E in this subgame. And so player 2 must be playing strategy CE, to which player 1's best response is A. And so this game's unique subgame perfect equilibrium is for player 1 to play A and player 2 to use CE. And so, because subgame perfect equilibrium requires that everyone be best responding in every subgame, we eliminate the possibility of a player using a non-credible threat to avoid some subgame. I claim that subgame perfect equilibrium is a refinement of Nash equilibrium, and that follows directly from the definition. We say that a subgame perfect equilibrium has to be a Nash equilibrium for every subgame, and that includes the root subgame, so it is a Nash equilibrium of the overall game. And since we know that every extensive form game has to have some pure strategy Nash equilibrium, it must be the case that every subtree has a pure strategy Nash equilibrium. And if we put together the equilibria from those subtrees and then pick a best response at the parent node, we get an equilibrium of the larger game. And so every perfect information extensive form game must have at least one subgame perfect Nash equilibrium. And better yet, we can compute subgame perfect equilibria using only the game tree without having to build the induced normal form. The basic idea for how to do that is we start at the bottom and work our way up, building subgame perfect equilibria for larger and larger subgames until we get all the way to the top. And as usual in computer science, this sort of algorithm that operates on a tree can be implemented recursively, and we call that recursive algorithm backwards induction. To run backwards induction on a game tree, we start by calling the function on the root node, and then we will loop through all of the actions available at that node, and since each action leads to some child node, we can recurse on that child node, and once each of the child nodes has returned its result, we will pick whichever one is best for the player making a decision at the current node. The recursive calls continue down the tree until we get to a terminal node, and at the terminal node we just return the utility tuple back to the parent, so that the parent can pick among the available actions whichever one gives the best utility for the player making a decision there. So let's try running backwards induction on this game tree, where this tree is a variant of the Bach or Stravinsky game, where now instead of the players simultaneously picking which concert to show up to, they are making an initial decision of which concert to buy tickets for, and player 1 buys their ticket first, and tells player 2 which ticket they bought, and now player 2 can buy a ticket to either of the concerts. And then each player subsequently has the decision of whether to go to the concert or to stay home. And again, player 2 observes player 1's choice before making their decision. The general preferences are based on player 1 liking Bach better and player 2 liking Stravinsky better, but they both prefer to go to the same concert, and so the best outcomes are the ones where they both go to Bach or both go to Stravinsky, and when they stay home they get a payoff of 0, or going to their favorite concert alone gives them 1, and going to the concert they don't like alone gives them -1. So if we run backwards induction, we'll start at the root and loop through its actions, and on the first of those we'll call backwards induction on the child node, and then we'll loop through its actions and call backwards induction on the first child, and so on until we have traversed all the way down to the leftmost leaf node of the game tree. From here, the terminal node will return the utility tuple, and so our backwards induction call at this level will get back 5, 3 as one of the possible options, and then it will continue its loop calling backwards induction on the next child, which will return 1, 0. And so now that it's gotten the result from all of its children, we need to decide which of those results is best for the player currently making a decision. At this node, the player making a decision is player 2, and so they're going to compare the player 2 utility in each of those tuples, which means in this case they're comparing 3 against 0, so they'd rather pick the option that gives them a utility of 3, and so from this node, the best action is G, and now this node will return to its parent the utility tuple corresponding to its best action. When we return 5, 3, that goes back to the parent node, which still needs to finish looping through its actions, so it will call backwards induction on the stay home action for player 1, and then this one will recurse on each of its available actions, and those will return the tuples 0, 1 and 0, 0. So at this decision node, since it belongs to player 2, we will pick the utility that is better for player 2, which is 0, and so this node will return the utility tuple 0, 0. And now, when we return to this level of the recursion, the loop through all of the actions has finished, and we got back the utility tuples 5, 3 and 0, 0. And since this is a player 1 decision node, we will pick the utility that is best for player 1. So 5 is better than 0, and they pick the tuple 5, 3, meaning that player 1's action at this decision node is to go to the concert, and we return the corresponding utility tuple to the parent node. Now this player 2 decision node continues to the next action in its loop, and we recurse down. This player 2 decision node is choosing between a utility of 1 or a utility of 0, and 1 is better. So we return the tuple 1, 1. Then we recurse down this path, and we're comparing a utility of 1 for player 2 with a utility of 0 for player 2. They prefer 1, so we pick the go action and return the tuple 0, 1. Now as we pop back up to this player 1 decision node, we compare the utility for player 1 in each of the 2 tuples we got back. 1 is better than 0, so they pick the go action and we return the tuple 1, 1. Now this node for player 2 has finished its loop through the actions and has gotten back 5, 3 and 1, 1. Since it's a player 2 decision node, we look at the utility for player 2. 3 is better than 1, so we pick the Bach action and return the utility tuple 5, 3. Now we're back to the root, but it has to finish its loop through the available actions, and so we'll recurse down the right-hand subtree, which will eventually lead us to here. We return -1, -1, and then we return -1, 0, and player 2 prefers 0 over -1, so here we pick the home action and return the -1, 0 tuple. From here, player 2 prefers 0 over -1, so they again pick home, and we return the tuple 0, 0. And then returning to the player 1 decision node, they compare 0 against -1 and pick home, which gets returned. Then we recurse down here. Player 2 compares 5 against 0 and picks go. Then we recurse here. Player 2 compares 1 against 0 and picks 1. Then player 1, selecting between utility tuples where they get 3 or 0, prefers 3. And we return to this node, where player 2 prefers 5 over 0. And now, all the way back at the root, we have finished looping through the actions, and our available options get us 5 or 3 for the player making the decision. And so player 1 chooses the option that gets them 5. And so in this game, the subgame perfect equilibrium gets the player's utilities of 5 and 3, and the actions that happen in the subgame perfect equilibrium are that they both buy tickets to and attend the Bach concert. But to write out the subgame perfect equilibrium profile, we have to specify the full strategies for both players, and the strategy involves the player's decision at every node where they can make a choice. And so the subgame perfect equilibrium profile is when player 1 plays the strategy B, G, G, H, G, and player 2 uses the strategy B, S, G, H, G, G, H, H, G, G. And in this game, that subgame perfect equilibrium turns out to be unique. It's not necessarily true that every game has a unique subgame perfect equilibrium profile. What that would look like is there could be some decision node where the options available to a player are equally good, And so they would be happy to pick either of their actions, and then we would get multiple equilibrium profiles corresponding to their different options at that point where they're indifferent. So the way this algorithm is set up, it will give us a subgame perfect equilibrium every time. We're always building up from the bottom of the tree, and at every possible opportunity we are picking a best response. And so as long as what we have lower down the tree is a subgame perfect equilibrium, then we'll pick the best option for whatever node we're at, and that will give us a subgame perfect equilibrium for that node, and we will continue all the way up to the root of the tree. The running time of this algorithm is linear in the size of the tree, because we had to explore every node in the game tree before we could figure out the optimal decision at the root. And on the one hand, that's great because we didn't have to build the induced normal form game. If we think about the size of that normal form game for this tree, since there are 15 decision nodes, and at each of those nodes there are 2 options, the induced normal form game would have 2 to the 15th profiles. And so exploring the whole game tree is way better than having to build and solve that payoff matrix. But also, for some games we might want to solve, the game tree itself can get really big. For example, I could write down the rules for checkers much more compactly than I could draw the entire game tree for all of checkers, because on any given turn a player might have dozens of available actions, and a game of checkers can have dozens or even hundreds of moves. And so sometimes just exploring the game tree is not efficient enough, and so we should think about whether there are ways we could refine backwards induction and find a subgame perfect equilibrium without having to recurse on every single node in the entire game tree. In the general case, there's not much we can do, but as we've seen before, the 2-player zero-sum case is often easier, and that turns out to also be the case with backwards induction, because in a zero-sum game, it is sometimes possible to be sure, without exploring certain nodes, that they are never going to be played in the subgame perfect equilibrium. For example, in this game tree, if we started following backwards induction, we would explore all of player 2's options from this decision node, and the one that player 2 likes best is the utility 0. And so now, when we are looping through the remainder of the actions available to player 1 at this node, we know that player 1 is going to pick the best action in terms of their utility, and so the actions that remain to be explored will only get picked if they can offer a utility that's better than 0. And when we start to explore down this next branch, and we see that one of player 2's options gets a utility of 1 for player 2, we now know that player 2's utility at this node will be at least 1, and since the game is zero-sum, that means player 1's utility, if the game gets here, is at most 1. It's totally possible that these other unknown options will do even better for player 2, but player 2 would only pick them if they give a higher utility than 1, which would mean a lower utility for player 1. And so as soon as we've seen this first option, we can say that if we get to this node, player 1's utility is less than or equal to -1. And since we already know that at the parent node, player 1 has an option that gets them 0, we know that player 1 will never pick this action, and so when the players follow the subgame perfect equilibrium, we will never traverse this branch of the tree, and so, without having to figure out exactly what are the strategies at all of the nodes in this portion of the tree, we can figure out the optimal moves under the path of play that will actually happen in the subgame perfect equilibrium, which means that we can cut off our recursion and avoid exploring all of these nodes. And there was nothing special about these being terminal nodes here. It could have been the case that these were all nodes in the middle of the game tree that returned these tuples after performing a search. And so it might be the case that once we get back this tuple, we can now avoid exploring huge regions of the game tree underneath these nodes. So to actually implement this, we need to slightly augment our backwards induction algorithm by keeping track of a lower bound on the utility for each player. And when we recurse, we will pass down that lower bound. So here, when we're looping through the actions for player 1, we got back a utility of 0, and so 0 is now a lower bound on player 1's utility if this node is reached. And so we can pass down that lower bound of 0 to any other actions that we're exploring below this node. And then, when we're looping through the actions here, if we find a violation of that lower bound, because here we found that player 1's utility from this node is at most -1, that means that we can cut off the rest of our search at this node, breaking out of this loop, because we know that the node above will never pick this action. And so in a two-player zero-sum perfect information game, we can augment our backwards induction algorithm using alpha-beta pruning, where alpha and beta are classic names for the lower bounds for the two players. And that will let us, if we happen to explore the nodes in the right order, avoid a lot of potential work and explore much less than the full game tree. And it's because of this backwards induction algorithm with alpha-beta pruning that we know that checkers under optimal play is always a draw.